Hey, we're back with round 2 of gas stoichiometry. So I'm just going to do another 2 problems that shows the differences between gas stoich and solution stoich. So here's the question. We've got 2.5 grams of ammonia that's made from 14.5 liters of hydrogen at 233 kilopascals. What temperature was the system under? Okay. Now, this one already gives you the balance reaction, so we don't need to do that. Yay. Let's write down what we know. We know we have 2.50 grams of ammonia. What goes with mass? Molar mass. So I need 1 nitrogen, 1401, and 3 hydrogens. That gives me 1704 grams per mole. One more time, because I think some people made some errors. That 2 doesn't affect the molar mass. The molar coefficients do not affect the molar mass. Okay. All right, what else do we know? Well, it says we've got 14.5 liters of hydrogen. Okay, perfect. At 233 kilopascals. Okay. All right, it wants temperature. Okay, we also have mole ratio. We're comparing these two. All right, so we'll go, 2 mole of nitrogen over 3 mole of hydrogen. Doesn't matter which way you do it. The last thing I need is, because this has been given to me, I've got pressure, temperature, and it's asking for, it's given me volume and pressure, and it's asking for temperature. I need the R constant. So that's the tricky thing. Like, when do you use the R constant? The R constant is 8.314 liters, and that's liters hydrogen, kPa hydrogen, mole hydrogen, liters kPa mole Kelvin hydrogen. So when do you know when to use kPa? If you have volume, it's a little bit different. All right, so if you have volume and you've got temperature and pressure, you need the R constant. If the question is saying STP or SATP, you don't need the R constant, but in this case we do. Okay, looks like we've got all of our variables. And what are we trying to solve? Temperature. So I need to start with my temperature on top. Where is my temperature? Where is the temperature? It is, where is it? No. There it is. Uh-oh, it's on the bottom. So I've got to flip the R constant to start. So we got mole hydrogen, Kelvin hydrogen, over 8.314 liters hydrogen, kPa hydrogen. Okay. Woo! All right, that's gone. All right, let's just start getting rid of some stuff that we don't need. Let's get rid of liters. So 14.5 liters hydrogen. Okay, that's going to get rid of that. Let's get rid of the kelvins. Oh, no, we've got to solve for kelvins. Let's get rid of, we can't really, there's 2 things on the bottom we got to get rid of. Okay, that's interesting. Okay, let's get rid of kilopascal, so 233 kPa hydrogen. Okay, that's gone. All right. So we're getting close. Now we got to get rid of moles of hydrogen. So let's use the mole ratio. So 2 mole of ammonia over 3 mole hydrogen. Okay. So the mole hydrogen cancels. All right. So now I'm going to run out of room here, so I'll have to squish it in. I got to get rid of moles of ammonia. So, there we go. That's moles of ammonia up here. So I'm going to flip that. No, I don't need to flip it. 1704 grams of ammonia over mole of ammonia. Mole of ammonia cancels, and I know I've run out of room, but I'm going to put on the bottom the grams. 2.50 grams over 1. Okay, so then the grams will cancel. Okay, I know that's kind of smushed, but that's where that goes. Okay, so everything on top, these are all of my on top stuff. So I'm going to go 14.5 times 233 times 2 times 1704. Okay, I'm going to divide that by the bottom, which is 8.314 times 3 times 2.5. Remember, because this 2.5 is on the bottom. Okay, actually, you know what? Just to make this a little bit better for everybody at home. Oop, not that. I will group this and I will shrink it a little bit, and then we can sneak this. Oop, I'm just going to rewrite that. We can sneak the mass down there. So it's all looking nice. 1 over 2.50 grams. Okay. Okay, and I get my final answer is 1,846 Kelvin. Well, that's pretty hot. Probably should have done this problem ahead of time. But that's what I get. I'm just going to double check that number is correct. 14.5 times 233 times 2 times 1704 divided by, in brackets, 3 times 8.314 times 2.5. No, that is correct. That's right. Okay, so proper sig figs, 1.85 times 10 to the 3 Kelvin. Well, that's super hot, but that's the answer. It's a smoking hot thing. All right. Okay, that's one problem. Let's try another one. If 5.6 grams of butane is burnt up, what volume of carbon dioxide is created at SATP? Okay, so we need the formula for butane, C4H10. Again, if you're not a super nerd like me and you don't have all these memorized, you can check page 4 and 5 in your data booklet. Burnt up is a hydrocarbon combustion, CO2 gas, H2O gas. Looks like we need a 4 there. We need a 5 there. And that gives me a fraction, right? So 4 and 5, so that gives me 8 oxygens plus another 5 is 13 oxygens. Now, I could go 13 over 2, right? 13 over 2, or I could go, what is that, 6.5? That would work. And if I'm looking at this problem, I don't really need to even balance the oxygen because this question is not even talking about anything to do with oxygen. So I'm just going to use the fraction 13 over 2 oxygen gas. You could go back and double everything. So you'd have 2, 13, 8, and 10. But you'll see in Chem 30 that fractions are used, and fractions are totally okay. So I'm just going to use a fraction there. Okay. If you don't like fractions, you could write 6.5. Same thing. All right, so we got 5.6 grams of butane. What goes with mass? Molar mass. So I need the molar mass of butane. That gives me 58.14 grams per mole. Okay. Don't need anything to do with oxygen. Don't need anything to do with water, but it says the carbon dioxide is at SATP. Now, I know not everybody probably remembers that, but SATP is 24.8 liters per mole. Okay. 24.8 liters per mole. It's asking for volume, and the last thing I need is the mole ratio between these two things, which is 1 mole butane over 4 mole carbon dioxide. Now, I was a little lazy, so I'm going to go back and I'm going to put in all the things that relate to it. Carbon dioxide, okay, this is butane, C4H10, C4H10, and C4H10. Okay. It's asking me to solve for liters, but liters of what? Carbon dioxide. Okay, I got to find liters carbon dioxide and start with that on top. Where is it? There it is. It's in the SATP constant that belongs to carbon dioxide. Okay, perfect. Go away, red box. Let's start with that. 24.8 liters carbon dioxide per mole carbon dioxide. Perfect. Okay, I got to get rid of moles carbon dioxide, so I'm going to use the mole ratio. Flip it, 4 mole carbon dioxide for every 1 mole C4H10. Okay, mole carbon dioxide cancel. Now I got to get rid of mole C4H10. I'm going to use the mole from molar mass right here. but I got to flip that to get it on top. C4H10 over 5814 grams C4H10. Okay, mole cancel. And then I'm going to use the mass to get rid of the mass right here. 5.67 grams. C4H10 over 1. Cancel, cancel. Okay, throwing the math in there, I get 24.8 times 4 times 5.67 divided by, in brackets, just 50, it's one thing on the bottom, 58.14. Okay, so 2 3 sig figs, the liters made is 9.67 liters. Okay, so another 2 practice questions. Hopefully you've seen, I'm sorry about this one. We got kind of like smushed up at the bottom there, but it does work out that if you see volume and pressure and it's asking about temperature, that is a warning that you're going to need the R constant. Okay, so I will be putting the R constant and SATP and STP are going to be copy pasted into every lesson that we have on gas Stoich, just so you can find it. And again, if a question straight up says SATP, well, you better make sure that it's linked to the substance it's talked about. And yesterday, we did one which had STP. And we started with the second question we did way down here. I know this is a while ago. We had an ammonia problem which had, look, pressure, temperature, and it's asking for volume. So we needed the R constant. So there's a time and a place for the R constant and SATP, STP. All right, that's the end of the lesson for today. So it's kind of a weird day. Today's Thursday.